Ladies and gentlemen, dear colleagues, welcome. My name is Deněk Hanzálek and you are watching the 42nd talk of the scheduling seminar. Today I'm happy to introduce Professor Dries Goossens from the Department of Business Informatics and Operations Management at Ghent University. Dries made his PhD in 2006 at KU Leuven with Fries Spieksma. He also works on combinator auctions and timetabling problems beside of sports scheduling, which is his main topic. Today he will speak about sports scheduling from consulting to science. So Dries, please go ahead. It's great to have you here and we are carefully looking forward what you will speak about.
Thank you. Thank you. I'm really honored to be able to do this seminar in this wonderful series that you set up. So sports scheduling from consulting to science. Let me start with explaining the problem of sports scheduling. So in sports scheduling, we are given a set of matches, a set of games, and a set of rounds. So a match is between two opponents, A against B, where A is the home team and B is the away team. And so the game is played at the venue of team A. So we get a set of matches and that follows from the tournament design. There are lots of tournament designs around. We will focus today on what we call the double round robin tournament, which is a tournament where each team plays against each other team twice. So once at home and once away. But there exist other tournaments. There is the knockout tournament, which is well known from Grand Slam tennis, for instance, where, well, if you lose one game, you're out. There are all kinds of hybrid tournaments. There is a Swiss tournament and so on. So the tournament determines the set of matches that need to be scheduled. And you also get a set of rounds. Rounds are time slots, typically weekends. And the sports scheduling problem in general is to decide which matches are scheduled on which rounds. A few key assumptions. One assumption very common in sports scheduling is that a team can play at most one game per round, right? And you see an example here of a schedule. This is a so-called time constraint schedule for a double round robin tournament with 6 teams. So teams labeled A to F, and you can see for every of the 10 rounds which games are scheduled to that round. This is what we call a time constraint schedule, which means that the number of rounds that has been given is exactly what you need to schedule all the games, right? Contrary to that, there is also a time relaxed schedule where you have more rounds than you strictly need, which means then, of course, that some teams will not play in some rounds. But the focus for today is on the time constraint schedules, so you get exactly the number of rounds that you need to schedule all the games. I would like to start with a brief history of sports scheduling. And I would go back to 1955, which is before I was born, actually, where this paper by Freund was published on round robin mathematics. And in this paper, Freund describes a way to schedule these round robin tournaments. It's pretty basic, we would say now. And actually, in retrospect, the idea is not totally novel because it actually goes back to this guy. This is Thomas Kirkman, a British reverend, who already in the 1800s came up with a way to construct feasible round-robin schedules with what we call now the clock method. Or it goes back to 1847. And schedules that result from that method are called canonical schedules. Now, you may be alarmed a bit because if you think about it, in 1847, there were no sports tournaments, right? The Olympics didn't exist yet. There was no football. There was no basketball. All these things had not been invented yet. There may have been some sports, but certainly not as a pastime or as a professional activity as it is now. So Kirkman didn't study sports schedules. He studied the schoolgirl problem. But it turns out that the things that he developed for that schoolgirl problem basically translate to sports scheduling. Okay, so after that first paper, we end up in the 1960s, 1970s, where there are a few papers. But basically, these decades are characterized by a lack of computational tools, right? People came up with integer programming formulations, binary formulations. But if you look at these papers, they typically say things like the existing algorithms are too large to handle on the available computer facilities, or even the cost of solving such a program by standard methods would most likely outweigh the savings derived from the improved schedule. Right, so that was the reality in the 1960s and 1970s, and I have added a picture here of the computing infrastructure of the days in 1975. You can imagine that the possibilities of this kind of machine are quite limited. Now, if we move to the 1980s, we get a number of papers that focus mostly on minimizing breaks. Now, a break is an important concept in sports scheduling, and I've added here the schedule for Belgium for the qualifiers for the upcoming Euro tournament. And as you can see here, it happens that Belgium plays 2 away games in a row. Round 3 and round 4, Belgium plays away. That's what we call a break. In this case, an away break. So 2 consecutive away games. And actually also a home break occurs here, and Belgium has 2 consecutive home games. So that's a home break. Now, typically in sports scheduling, breaks are not appreciated. It's said that it gives a disadvantage if it's an away game, or perhaps an advantage if it's a home game, that it attracts fewer people at the stadium. I mean, lots of things have been said about breaks. Not so much has been shown empirically, I should confess, but breaks are important, and typically people in sports scheduling want to minimize these breaks. It's not so very hard to see that, of course, you do need breaks. Otherwise, if you have more than 2 teams, well, the third team would not be able to play against the first or the second team unless it has at some point a break in the schedule. So that was the important question in the 1980s, and especially Dominique de Werra has written a few seminal papers where he makes the link with graph theory. We can see a single round robin tournament as a 1 factorization of the complete graph, where every 1 factor corresponds with games to be scheduled on 1 round. And of course, the nodes in that graph correspond with the teams. De Werra also has results on the minimal number of breaks and on ways to achieve schedules that have that number of breaks. And if you put an orientation on the edges, if you make them arcs, you can further exploit that to minimize breaks. Okay, we have to wait for the late 1990s to see the first real-life applications. And of course, that goes together with the increasing computer power and also with some methodological breakthroughs. So at the late 90s, Nemhauser and Trick realized that you could decompose this problem by first looking at the home advantage, first fixing the home advantage for every team, and then looking at the opponents, or the other way around. So this has been a methodological breakthrough. But until that time, manual solutions in practice were still quite dominant. There is a story about Henry and Holly Stevenson, a story that I heard from Mike Trick. These people they were married, and they have been scheduling the Major League Baseball competition for 25 years by hand. So really a pen and paper kind of approach. And eventually, after years of effort, Mike Trick came up with a method that put them out of business, so to speak. But it's amazing how these manual planners really understood the scheduling. They saw patterns, they saw structures in this problem that none of us OR people see. And so for a long time, they have been very dominant. They have been craftspeople, so to speak. And then at the turn of the century, we enter what I call the age of consulting. You see a lot of papers on sports scheduling, all describing a particular problem, like the Swedish handball Federation, Belgian soccer, soccer in Ecuador, German basketball. There are lots of these kind of papers. And what's typical about these papers, they describe one particular problem. They come up with an algorithm for that problem, a method for that problem. They run that method and compare with the manual scheduler, the Stevensons of the case. And then they find out that their carefully designed method outperforms the manual solution. They are happy with that, and they publish the paper. And of course, this is nice because it's the kind of research that most of us like, that has an impact on practice, that substantially improves well, the practice of sports scheduling, that delivers schedules that are better for any stakeholder, for the fans, for the teams, whatever. But, and I'm not trying to throw rocks at people because, well, I have also written these kind of papers. I think that is consulting, but it's not really science. It's not really what we need as an academic community, or at least we can do better as an academic community. I think it lacks benchmarking. All these specific case studies with tailor-made algorithms have the disadvantage that the problem instances are rarely shared. To some extent, that is because of confidentiality issues, and the football associations or other sports associations are typically not so happy to share the details of this problem with the world. But still, I have the impression that the authors also didn't bother too much by publishing perhaps not a real problem instance, but very similar problem instances. And also the algorithms are almost never benchmarked. They are just run on this particular instance and then not used again. And no other algorithms have been run on that instance. So that is problematic because we don't understand, we don't learn when algorithms work well and under what circumstances, for what type of problems do they work well, why do they work well, or why do they not work well? We don't know. And besides, the question also arises whether it's possible to develop a more general solver. Is it really necessary that for every problem we develop a tailor-made algorithm, or could there be approaches that work more generally, that can handle a wider variety of sports scheduling problems? Yeah. So this is actually my goal for today, to take you from the age of consulting to the real science. And I will describe the approach that we followed in 5 steps, where step 1 is to come up with a classification scheme to create some order in the chaos of all these different sports scheduling problems. Second step is to develop a standard problem instance data format that allows us to easily share problem instances. A third step is to develop a benchmark set of instances that we can use to compare algorithms. A fourth step is to come up with more general sports scheduling solvers. And then our final step is to test them on the benchmark set and to, well, do algorithm selection to figure out which algorithms work well on which type of instances and get insights from that and really learn something. All right, so the first step is this classification scheme. So you must imagine that there are so many different sports scheduling problems, and they differ in the constraints that they use, they differ in the objective function that they have, they differ in the competition format that they deal with. So we came up with this classification scheme that uses 3 fields, alpha for the competition format, beta for the constraints in use, and gamma for the objective function. And of course, there are many schedulers in the audience, so they will immediately realize that this was inspired by the famous notation for the machine scheduling problem by Graham et al. So we tried to do something similar here for sports. So by looking at the papers in the literature, we came up with this classification, which considers for alpha for the competition format, a label alpha 1 for the tournament structure, which can be K round robin. So again, round robin is a tournament where every team plays against every other team the same number of times, K times. but also variants like decay bipartite round robin and also non-round robin formats. But the focus is still mostly on round robin. Alpha 2 shows whether the timetable is constrained using just as many rounds as you need to schedule everything, or time relaxed, using more rounds than you strictly need. And Alpha 3 is a symmetry factor. Think about a double round robin tournament. You play against every team twice. So should it be phased? Should you play against every opponent once before you can meet an opponent for the second time? If that's true, it's phased. And you could go even further where there is some kind of symmetry between the two parts. It could be mirrored, or other symmetry structures are also possible. So then about the competition format. We looked at the constraints that we saw in the literature, and we grouped them into 5 groups, where each group has a number of typical constraints. I'm of course not going to go over all these different constraints, but just give you the idea of the groups. We have a group of capacity constraints, which deal with whether or not the stadium of a team is available at a particular round. So can this team play a home game or not? We have game constraints. Game constraints are about specific matches. Is it possible to have a game A against B on round R? We have break constraints, and they regulate the breaks. Now remember, a break is when a team has 2 consecutive home games or 2 consecutive away games. Typically, a break constraint could minimize the number of breaks that you have in a tournament, in a schedule. We have fairness constraints. They typically balance all the unfair things you can have related to a schedule, like, for instance, the carryover effect, or they make sure that every team at any point in time has played more or less the same number of home games and that kind of things. And finally, there are separation constraints. They put a constraint on the time between 2 games between the same teams, right? So A plays against B, B plays against A. How much time should be in between these 2 games? All right. Now, for each such constraint, we define, or we let the problem owner indicate whether or not it's whether it's hard or a soft constraint, right? So hard constraints have to be satisfied at all costs. Soft constraints can be violated, but then of course you pay a penalty. We also need to define the deviation vector. We have to measure exactly what that means, not satisfying a constraint, and what is deviating from that constraint. And then we have to score that deviation by a cost function. That could be simply the sum of all the deviations, could be the maximum deviation or the minimum deviation. We have 5 possible cost functions. And we also have a weight for the constraint that allows us, for soft constraint, to indicate how bad it is if you cannot satisfy that constraint. Okay, and then the final field is the objective function, right? We could have no objective function, making it basically a constraint satisfaction problem, or minimize the breaks, minimize the travel distance, minimize costs for certain games, minimize carryover effect, and finally, the most common one, minimize the sum of the soft constraint violations. Okay, and putting all this together, we get this classification with the 3 fields, alpha, beta, gamma, and their subfields, and this can basically categorize which kind of sports scheduling problem we are facing. Okay, now with this classification scheme, we went to look at the literature, and we basically went over all the papers there and labeled the problem that they describe in the paper with this classification scheme. So as you can see, for instance, this paper by Bao and Trick has a double round robin tournament with a relaxed timetable, no particular symmetry, and it has constraints of the type CA3 and SE1, and the TR objective function. So we did that for basically everything we could find in the literature. And we also developed a website which has an online query tool. So you see all the different fields and values there. And you can indicate by clicking it green that you are looking for a paper in which these particular constraints appear. Or you can make also a constraint or an objective function red if you want to exclude that particular constraint or objective function or competition format, right? And then the query tool will list all the papers that have sports scheduling problems with your desired specifications. So this is very convenient. If you have a problem from practice and you want to figure out quickly which papers in the literature have a similar problem or similar characteristics, you can do that with our website, which you can find well, at the address at the bottom. Okay, so that's for the first step. And amongst all these different sports scheduling problems, we have created some structure, some order with this classification. Second step is to generate a standard problem instance data format. In our case, we opted for XML. I'm aware that there are other options. And actually, before we did this, there was an attempt to do it with text-based formats, also in sports scheduling. But I think XML, in the end, is the more comprehensive one. It allows us to structure problems in a way that we can still humanly read them, but at the same time also be efficient to process them with program code. So we have three types of data files, data formats. We have one for an instance that describes the whole problem instance. We have one for a solution, and we have one for a bound, if you have found a lower bound for a particular problem. Now, on our website, you can consult the problem instances that we found in the literature and that we put on the website ourselves, but you can also create your own problem. You can do that in two ways. Either you make use of our web application, a little form that you can fill out where you can specify all the things about your particular sports scheduling problem. And then this website automatically generates an XML file, which is according to our classification system, our data format. Or we also have a C++ library that you can use. It's open source, it's freely available to read, write, and validate these XML files. So we have this problem instance repository where we try to gather as many of these sports scheduling problems from the literature as we could with their classification. And for each of these problems, we keep track of the current best solution that anyone has found, and also the current best lower bound, if available, and also a history. So if you at some point have found a better solution for any of these instances, you can upload that solution to our website, and it will be validated and it will appear as the best found solution or as part of the history. The instances in red are not yet solved to optimality. If you see a line in green, then it means that an optimal solution has been found for that instance. Okay, so we also have an online validator where you can select your problem instance. And the instances that you see here are for the well-known traveling tournament problem, which was on a website by Mike Trick until, well, recently. He transferred basically his data to our website. So you can select your problem instance file or generate or upload your own. You can generate or upload your solution file. And then our validator is going to check whether you have satisfied all these constraints. So basically it will validate the solution, and it will show you how many hard constraints have been violated, how many soft constraints have been violated, and what the penalty would be of the soft constraints that have been violated. So I think this is important for the research community to have a standard way of checking and validating whether your solution is indeed correct and well, hopefully better than whatever anyone found before you. Okay. So that was the second step. Now the third step is to come up with a set of instances that can serve as a benchmark, that can serve to compare your algorithm with other algorithms. And to do that, well, we started from our classification, but we didn't consider all possible objective functions, constraints, tournament formats. We had to make a little selection there. So we opted for the most common ones, which is a time-constrained double round-robin tournament, phased or not, where we selected 9 constraint types from the list. And as an objective function, we opted for the most common one, namely where you have to satisfy all the hard constraint and you minimize the sum of the soft constraint penalties for the constraints that you violated. So this is a quite common choice, I think. And we gathered all the problem instances that we could find that satisfy that scope. And you can see them there listed. Okay, now that on itself is not really a benchmark. First of all, okay, they are realistic because these instances come from practice. That is nice. We are not so sure if they are really challenging because many of them have not been tackled with different algorithms. But for sure, they are not so diverse. And we actually also want a diverse set of realistic instances. So how will we do that? Well, we first of all need to characterize problem instances. And we do that using what we call features. A feature is basically just any measurable property of a problem instance. Now, the features that we chose were the number of teams that play in that competition, the symmetry, whether or not it's phased, and the number of each constraint type that is in that problem instance. So for instance, the number of CA1 constraint, the number of break constraint B or 1 constraints for hard and for soft. So this is a pretty high level description of the problem. I think that has advantages as well. I'll get back to that later. So looking at these features, you can make a table and look at the instances that we found in practice, that we found in the literature, and see how they scored on each of these features. So you can see we have found instances with 10 teams up to 22 teams, where on average it's 15 teams and so on. Now that doesn't say all that much, of course, this kind of table. So we work towards a visualization of this problem, of this set of problem instances, where we can start from the feature vector, these 18 features that we have as a vector. We can also display them in, well, the feature space, but that feature space has 18 dimensions, of course. And I don't know about you, but my 18-dimensional drawing skills are not so very good. It's not fun to work with, it's not easy to work with. So it's not uncommon to reduce that to 2 dimensions, which is much easier for us to process. We can do that using principal component analysis. Now, of course, this whole technique of transferring a feature vector into a 2D space is not something that we discovered. This is described by Smith-Miles and other co-authors, for instance, in this paper and also many following papers. It's known as instance space analysis. So we basically applied the main ideas of that to the domain of sports scheduling. Then we get this plot, which has all the problem instances that we found from the literature. And it also has this red, well, convex hull around it, which indicates what, well, where the boundaries are from a practical point of view, what kind of values for the features that we have seen in practice, of course, after principal component analysis. Now, as you can see, they may be realistic. Well, they are realistic. They are life-based. They may be challenging, but this is not a diverse set of instances. You see that in some areas we have lots of instances, but there are also lots of areas where we have no instance at all. So ideally, we would like to fill the gaps in this instance space. Ideally, we would like to come up with an instance on the gray dots that are here in the form of a lattice. Of course, only the gray dots within the red convex hull, because the other ones are not realistic. So that would be our target. How can we come up with a set of instances that match these gray dots that are diverse and at the same time realistic, because they are in the red convex hull, and hopefully also challenging? So we do that with an IP approach. And we actually try to come up with values for the features that are such that we reach that target, that we reach that gray dot. So in that IP model, the variables are the values for the features. How many constraints of that type do I have as hard constraints? How many constraints of that type do I have as soft constraint? How many teams and so on? So we try to set the feature values and then using the PCA components, translate that to a dot in our space, where we want to minimize the deviation from the target, right? So we have S and E variables to indicate the slack and the excess on both axes. We want to minimize these differences from the target. Okay, so the F variables are the values of the features, which of course we normalize in PCA. So that's why we need the G here. And the model on the right does exactly that. I must say we did add a number of other constraints to make sure that we didn't have too many different features or not too many features of one particular type and so on. So if you solve that model, you will get feature values that represent a problem instance on that target. But of course, these feature values are still not a problem instance. We still have to translate that to specific constraints. We have to indicate exactly which of these CA2 constraints are there. What parameters do we have? What numbers are there? So to do that, we start from a basic schedule where we kind of build these constraints around it. This has the advantage that at least we know for sure that a feasible solution exists. It would be a bit unpleasant to generate a number of instances for which we don't really know if there is a feasible solution. So that is then solved. Okay. And then the final check would be to check whether these instances are actually challenging. Are they difficult? So what we did was we built an IP solver, we built a constraint programming solver, and we also built a fix and optimize methoristic. And we just released these basic approaches to the instances, and well, we saw what happened. So the result for the instances that we generated was that after 1 hour, IP found 12 feasible solutions, CP found 16 feasible solutions, and fix and optimize found 15 feasible solutions out of the 45, and none of them with proven optimality. So that was for us kind of a hint that, well, they were not too easy. None of them could be solved easily within a short time. Then again, they were also not extremely difficult because for most, already a feasible solution was found after 1 hour. And also we checked whether we could find different solutions with different objective values to make them a bit more interesting. Okay, so this is how we constructed this benchmark set, this set of benchmark instances. Now the next step is to see how algorithms score on this benchmark. Now I told you so far we don't really have general solvers. We have all these separate case studies, each with their particular approach, but not really general solvers. So how do you come up with general solvers? So here our idea was, well, let's not do that ourselves. Let's have other people do that. People who are perhaps most likely much better at this than we, right? So we decided to organize an international timetabling competition. Now, international timetabling competitions, that is also not new. There is a history of these timetabling competitions. But in 2021, we thought, okay, now it's time for sports timetabling, for sports scheduling. So we organized this competition. We had our set of benchmark instances as the instances that needed to be solved in the competition. And we invited researchers from everywhere to come up with an algorithm that was able to solve these instances. The instances were released in 3 different groups: an early group, a middle group, and a late group. So the early group was released somewhere in October 2020, which gave the researchers several months still to develop the solver, whereas the late group was released just 2 weeks before the deadline. But there was one deadline, so all the instances needed to be solved by that deadline. We had a number of rules in that competition that are perhaps important to know. First of all, we had no computation time limit. and people could use as much computation time as they wanted, just they had to make sure that they respected the final deadline. And also no technology restrictions. You could use whatever infrastructure you needed, whatever package, if you want to use Gurobi, Cplex, whatever, you could do what you like. The idea is also that we as organizers do not run any algorithm code. So you run it by yourself. That is, of course, from our perspective as organizers, easy, because the first international timetabling competitions have struggled with that a lot. They wanted to run code that someone else has written in a different machine and so on, and that led to lots of discussions and lots of effort. So we wanted to avoid that altogether. But we did want the same version of the algorithm to be used for all instances. That was the main idea, to develop some kind of general solver that would be able to at least tackle all these instances in the benchmark set. Now, for each instance, the competitors in the competition could get points. So if you had the algorithm that for that instance was the best algorithm, you collect, if it was an early instance, 10 points. If you were second, you collect 7 points and so on. So for each of these instances, you could collect points. And as you can see, the late instances where you only got 2 weeks get a higher weight compared to the early instances for which you actually had months of time. So we used that point scoring method to rank all the participants. And we had 13 participants. We were actually quite happy with that. It means that we, at the same time, have 13 algorithms that have been developed, let's say, for us. And this was the ranking. And so UOS, which is the University of Southampton, won this competition before Udine and Saturn. As you can see, most instances were solved. Well, a feasible solution was found for most instances. University of Southampton found the best solution for 21 instances, and Udine as a second only for 4, but they were able to solve many instances and get close to the best found solution. Okay, so that was, let's say, a cheap way to collect a number of general sports scheduling algorithms. We basically let other people do that for us. Now, final step is, well, to get some insight in how these algorithms perform. So we realized that the 45 instances that we used for the timetabling competition are actually a bit, well, it's actually a bit a low number to do a serious analysis. So we decided to go for another computational experiment and generate more instances. And we asked to the participants of the ITC competition who would like to continue with this, who would like to further use this algorithm for this. So 7 of the participants agreed to further work with us, and we also generated 1 new algorithm. Now, these 7 algorithms and the new one are listed here on the right. And as you can see, they're quite different. There is modal, which is basically an IP approach, a very advanced IP approach. There is goal, which uses fix and optimize. We have adaptive large neighborhood search with DES. We also have the UOS, the winner of the ITC. We have simulated annealing with Udine. We also have a CP and SAT solver. We have pseudo-Boolean optimization. And we have with the final algorithm, which is the one that we newly generated, a first break and heuristic schedule, which is in line with the famous method of Nemhauser and Trick, which is based on the decomposition of the problem. First look at who plays home, and then look at who will be the opponent. So we had this interesting portfolio of different approaches that we could test. And as I said, the 45 instances that we had for the competition, they were not enough. So we used the same method to generate additional problem instances. We generated 518 additional problem instances. You can see them as the gray dots in this figure, whereas the blue triangles are the instances that we have used for the timetabling competition. Okay. Now, as you can imagine, running all this takes a lot of computation time, but we were happy to copy the rules for the timetabling competition, namely that every algorithm is run on the infrastructure available at the institution where they were developed. From a practical point of view, this makes everything much more feasible than doing one big experiment on the same computer. We gave every algorithm 2 weeks to solve these 518 instances. Again, there was no particular time limit on a specific instance. The idea was just that in the 2 weeks, you should have tackled the 518 instances. I must say, if you look at the computation time that was used, on the left, the wall time, and on the right, the CPU time, which takes into account the number of cores that were used, you can see that there are differences between these algorithms. Like, for instance, UOS, you can see that they use really a lot of computation time, whereas DES, on the left, they didn't use much computation time at all. The same for UOR, which is actually the reprograde algorithm. So there were differences there, and that can play a role, of course. The more computation time you give, the better an algorithm can perform. That is obvious. On the other hand, we do think that we gave sufficient computation time to most algorithms. Okay, looking at how they perform, we can at the left see the absolute performance gap. So the difference between the result that these algorithms got and the best value that we found for that instance. And if you look at that, you can see that actually Udine, who is second in the timetable competition, manages to find good solutions for almost all instances. And to some extent, also the FBHS, the first break heuristically schedule approach, also get quite good results, but not for all instances. And if you look at the right, you can see how many instances a feasible solution was found. So if you look at Udine there, they managed to find a feasible solution for almost all the instances, whereas the first break heuristically schedule method fails in finding a feasible solution for quite a lot of these instances. You also can see that modal, which is the IP approach, sometimes does very well, but also for a lot of instances is quite lost. Now, we can, of course, also draw the performance of these algorithms in the instance space and see for what kind of problem instances the algorithms score well. And as you can see, I mean, it's predominantly green, the green of Udine, of the Udine solver, which is more or less all around. Although in the area at the right and at the bottom, you can see the purple of the first break heuristically scheduled algorithm. So in these regions, that algorithm performs quite well. And in the middle, you can see a number of blue dots. And so there, the goal algorithm is the best performing algorithm. You also see these pink dots at the bottom left. That's where we have a tie between algorithms. And in fact, it turns out that these are the easy instances where several algorithms manage to find the same, in some cases, even optimal solution. And in the top left, you see these gray crosses. They correspond to instances that could not be solved. So where we found no feasible solution at all. Now, this is a general overview, but you can, of course, create this kind of footprint for every algorithm separately, which is what we have done here. So on the left, you can see the algorithm footprint of the Udine solver. And the darker blue, the better they perform. Again, the gray crosses are where they didn't find a feasible solution, and the light blue is where they did not get a very good solution relative to the other algorithms in the portfolio. So you can see that Udine actually does very well, and almost everywhere they come up with good solutions. And we can also match this to the presence of the features. So on the right, you can see where the phased problem instances are, top right. And you can see that in that area of phased instances, Udine handles that quite well. And also where we see this SE1 soft constraint. And that is also a constraint that Udine is able to handle well, which is not a total surprise because they included a neighborhood which focuses specifically on that phased characteristic. So you can see here that it indeed worked well. This would be the footprint for the first break heuristically schedule. And you can see now that It doesn't do well on the left part. You see lots of instances for which it doesn't find a feasible solution, but it works very well on the right, bottom right, which is the area that corresponds with the presence of the break constraint. And BR2 is a break constraint and as a soft constraint. Now, actually, that surprised us a little bit because with this method being a decomposition method where we first fix the home advantage should actually work well also for a hard constraint on the brakes, because you settle the brakes first and then you look at the opponents. And this is not what showed from the comparison from that footprint. So this gave us a hint that, well, where we can further improve that algorithm. And I'm not going to show you all these footprints, but I'll just show you the one of Modal. Modal is the IP solver. And as you can see, well, it didn't do quite well. It turns out that these sports scheduling problems are still quite difficult to digest for an IP solver. We see many instances where it didn't find a feasible solution. And if it did find a feasible solution, it's often quite far from the best solution found, especially that region with the phased characteristic and where the presence of these hard break 2 constraints is not something that IP digests well. You do see a number of these dark blue instances there at the bottom. So there it performs well, but it turns out that are actually the easy instances. Also, most of the other solvers found a good solution there. Okay, a final question is, now, can we predict which algorithm will work well on which instance? And for that, we developed a number of classification models and also regression variants. So I guess you know the nearest neighbor, random forest, gradient boosted trees, and support vector machines classification models, which is a general classification model that will tell you which algorithm is predicted to work best. We also have regression variants that are models for each algorithm separately and try to predict the score of how that algorithm will work. And then you can pick the algorithm with the best score. And we also implemented majority voting over these 8 models and variants. And so these are the results on the left, on the validation set, on the right, the test set. The test set in this case are the instances from the timetabling competition. The validation set is 20% chosen from the 518 additional instances. We see in red the number of feasible solutions, in green the relative performance gap, and in blue the accuracy. And so how often does it predict the right, well, the best performing algorithm? So on the left of that figure, we have the algorithms separately, where you can see that actually, especially Houdini and first break heuristically schedule have a good performance. They contribute a lot to the portfolio. And then on the right side of these tables, you see how the classifiers work. And actually, they do quite well. We've seen from the footprints that there is complementarity. There are regions where one algorithm performs well, and there are regions where another one performs well. And these classifiers can, of course, spot this and exploit it to predict which one is going to work best and to get better results than with any of the algorithms individually. So we get an accuracy of, well, in the case of the validation set, about 30% better than the best algorithm. And even in the test set, still about 20% better than the best algorithm. So this means that these models perform quite well, and we are quite well able to exploit the complementarities between the algorithms and to predict which algorithm will work well. And actually also from a practical point of view, this is interesting, because if you remember, the features that we chose are quite high level. So it's not so difficult to predict beforehand what kind of instance you will face, right? Most competitions can tell beforehand, okay, we will have this and this and this type of constraint. We will have more or less so many of this type, so many of this type, so many of this type, right? So these are things that problem owners can know long beforehand and plug into this system, which will then recommend them the best approach to follow. Yeah, we also looked at which features are important in making that decision. And it turns out that this separation soft constraint and also the break soft constraints are very important, and that they determine to a large extent which algorithm will be predicted. Okay, I have more or less reached the end of my talk, where I hope I have convinced you that we have made a step from consulting, where, well, the idea is find a customer with a particular problem, develop your clever tailor-made algorithm, and celebrate your success of beating this person who does it just by hand, by pen and paper, and certainly not disclose the problem specifics. This is what consultants do. If you would do that, you might lose your customer, which is nice for a beginning field of research. But of course, after a few decades, I think we should move to the science part, where we share our problem instances, and we contributed to this by making this XML instance repository available, where we should test our approach on other instances as well, and not just the one particular instance that we like, but also others. And for that, we have developed this benchmark instance set, and where we can actually learn what the strengths and weaknesses are of algorithms using these footprints, and come altogether to a better understanding and a way to improve, to further improve our algorithms. I have this slide with references of papers that I have mentioned, papers by ourselves, by co-authors who have worked on the algorithms for the competition. But I would certainly not want to forget this last slide, where I would like to thank my co-authors, and in particular, David van Bulk, who is a postdoc researcher at our research group, who has been doing, honestly, most of all the work that I have described here, and other co-authors who have been very kind to work on the development of the algorithms that we have used and tested. I also want to thank my sports team, my PhD researchers here at the group who work on sports-related problems. I would like to thank all participants to the ITC timetabling competition. I would also like to thank the Euro working groups OR in Sports and Patat for being so kind to sponsor this timetabling competition. Okay, thank you.
Okay, thank you, Dries. So now everybody should be able to unmute his mic or her mic. So please go ahead and ask questions if you have some. If nobody does so, first of all, thank you for a nice talk. And second, may I ask you to go to slide number 45? There was some result of this slide.
This one.
So we see this heuristic algorithm, FBHS, right?
Yes.
On the right side, in the middle, there is quite a regular pattern of, let's say, successful solutions. These are nearly squares, right? So do you have any explanation for why these instances with those specific parameters of those feature vectors were easier for this algorithm to solve? Or
well, as you see from the picture on the right, they are the type of instances that have this BR2 soft constraint, right? That's a constraint on the breaks. So there is a soft constraint on the number of breaks that a schedule can have. Now, it's on itself not so surprising that it would handle breaks well, because this algorithm is a decomposition algorithm. It first fixes the home advantage, which includes the breaks. If you know the home advantage, you know when you will have a break. Right, so if these breaks are very important, that's a very clever thing to do, because you want to fix that, to settle that first. And then as a second step, it looks at the opponents, right? So in that sense, it explains why it handles these breaks well. The thing that surprised us a bit is that if you have the breaks as a hard constraint, it doesn't work so well anymore, which I think it should still, because it still has this decomposition approach, should still work well. So that's something we are looking into, how we can further improve that.
Yeah, and we don't have any simple explanation on what are the features on vertical and horizontal axis, right? So this is a mixture of.
Yes, that's the principal component analysis who has mixed this a bit. Of course, we know the vectors for that, but yeah, this is a bit more difficult to see.
Yeah, but that surprises me that in the middle of this bubble, you have quite, let's say, equidistant points, right?
Yeah. This so I mean, the features have been normalized, right? So what you would see in the middle of the picture are, well, the least extreme feature values, right? The more you go to the outside, the more you have extreme feature values. So,
okay,
yeah.
All right, thank you. So, any other question? Nasser is going to ask something.
I have a question. Did you publish these three-dimensional notations that you presented for sport scheduling in a paper?
Yes, I did. This is actually described in this paper here in eJOR. It's the second one listed here. It's the Robin X free field classification.
Oh, wonderful. Thank you very much. That was really helpful.
You're welcome.
Let me ask out of curiosity, of all the contenders, how many of them were non-European? So you had any American, Canadian, Brazilian, or Singaporean?
Not so many. I mean, the most, if I go through the list of competitors here, I think most of them are European. I mean, Saturn is a Russian team, and there is a Brazilian team involved here as well. But most of them are European, which is perhaps not so crazy in the sense that it was mainly advertised by the Euro working groups, Patat and ORN Sports, who of course have a focus on Europe.
Yeah, it's probably my fault. I should have told Mike Trick. Actually, I have asked Mike Trick, invited him a year ago to give a presentation in this conference, but in this series, but he is nowadays a dean, so I'm not quite sure how much he probably does class scheduling and not sports scheduling anymore. So, but Mike Trick was very enthusiastic about this, but he didn't show up today, I think.
Right. Any other question? So if I can ask a little bit in a broader sense, today we spoke about these two round-robin tournaments, right? Do you have any idea if there are some surveys on, let's say, other problems as well? So like something like larger picture of this domain, or any books written, or...
Yeah, there are round-robin tournaments, single, double, triple. And by far, I think they are the most interesting from a scheduling perspective. Because, I mean, think about it, a knockout tournament, a direct knockout tournament, like they do in Grand Slam tennis.
Yeah.
There is not so much you can schedule there because there is this order of games that is fixed. I mean, you're not going to play the semifinal before you play the quarterfinal. So there is less of a problem there than in the round-robin tournaments, which is why, as far as I'm aware, the sports scheduling literature has focused so much on round-robin tournaments. Although there is a new variant arising, which is the Swiss tournament, where also Celso has worked on recently, and which is also an interesting tournament in the sense that it has a fixed number of rounds. But these rounds are not enough to schedule all games against all opponents. So you'll have to choose against who you schedule a game and which games are not there, right? So you will not play against every opponent anymore. So this also create some scheduling challenges.
Okay, so we have had a talk by Nick Carter, right? He spoke about like dynamic organization of the schedule, so that even at the last round, the teams are motivated to play, let's say, competitively, right?
Yeah, that is a very interesting way to go. Because typically in sports scheduling and also in the things that I discussed today, everything is static, right? You decide beginning of the season, all the games, and then you play them. Of course, if you would do that in a dynamic way and you schedule a number of games and then see what the results are or what other constraints arise, or you get more information and use that to then progressively schedule next parts of the season. And that dynamic approach is indeed very interesting. Although so far I have not been successful in implementing that kind of wild idea in practice. Okay, it is used in chess and in some esports to some extent, but most of the classic sports, especially football, are very reluctant to go that way. And in some sense, it's still a very conservative environment, I guess.
Okay.
I suppose that the main advantage of that is, in the dynamic one, is that halfway through the tournament, you sort of can predict better who the top finalists are going to be. And you want, of course, those teams to play at the end against each other, because you are, a big objective here is in the United States, you want to maximize the number of eyeballs that you have on TV. And if you can postpone the knowledge of who is going to win the tournament and postpone it all the way to the end, that's actually a very that implies a lot of money. There is a lot of money that can be made that way.
You're totally right. And I have talked with the Belgian Football Association last year, because, as you know, the World Cup football was played in November, December this time, which is kind of in the middle of the domestic league, which means that the domestic league was interrupted for a number of weeks anyway. So I wanted to seize that opportunity to say, well, let's just schedule the first half of the season until the World Cup, and only then schedule the second half, taking into account all this extra knowledge that we have about which teams perform well, also which teams are still active in European leagues, in Champions League, Europa League, and so on. We could make a much better schedule for the second half of the season after the World Cup. But I was not successful in convincing them, so they remained with the static version. But I'm, as a scheduler, very much convinced of the advantages of the dynamic schedule.
I have another question about the breaks. As far as I remember, there are different types of breaks, and some are more damaging than others. So when you want to minimize the number of breaks, let's say, I presume that you have a sequence of 2 away games, that's a break. 2 home games, is that 2 consecutive home games, is that also the same level of a break as the 2 consecutive away games? So you have any break counts evenly. And when you say you have soft constraints about breaks, how are you optimizing then with soft constraints? Are you putting some weight to the objective, the number of breaks, and you have a weight and that goes in the objective function? How do you incorporate soft constraints?
Yeah. So we do consider breaks equally bad, right? Home break or away break. And the idea being, if some team has a home break, then there must be another team that has an away break, right? So in the end, they equal each other in number. About the soft constraints, yes, indeed, we count the number of breaks, and if you exceed that particular limit, we count the deviation. So for every extra break that you use, be it per team or for the schedule in a whole, we add to the penalty in the objective function. Yeah.
I have a short comment.
Yeah.
In Chile, they have a tournament that is organized in 2 parts. It's a phased tournament, and they scheduled 2 parts separately, so they can use this idea of dynamic scheduling the second part of the tournament in order to achieve a second goal, for instance, maximize revenues. Since they know the positions of the teams, for instance, in the second half. Okay, so in Chile they do it. This is more or less what you were proposing, Dries, for the Belgian tournament.
Yeah, it's interesting to hear that at least in Chile the Football Association is a bit more clever than the Belgian one.
Yeah, they have other problems in Chile. Okay, but at least they can do this. Okay, but what we are doing with dynamic scheduling is in electronic sports. Okay, esports. Okay, and this is different because, as I said, it's more or less like in chess and Go, where you have all participants together, so you don't have troubles. So you can reschedule with everybody's together, so you don't have too much logistics involved.
Yeah, exactly. Yeah.
Okay, but in the past, we tried in Brazil to use the idea of dynamic schedule, but it was too complicated, and there were some reactions by the participating teams. Okay, the teams do not like it.
Yeah.
They want some previsibility, what's going to happen. They don't like it.
Yeah, I have heard that concern as well from teams, let's say teams that are bottom teams halfway through the season. Yeah, they could be scared that knowledge could be used to further disadvantage them. Whereas if you don't know that in the beginning of the season, well, it's perceived as more fair. I'm not sure if it needs to be like that, but that's a concern of these teams.
Yeah. And there's another thing also, because you are interested in the first places in the classification ranking, but in some countries, in Brazil, you are also interested in the lowest positions, because these teams will be degraded to the second division. So teams are fighting in the highest positions, but they are also fighting in the lowest positions. So there's fighting in both streams of the classification ranking. Okay, so it's not only the first positions that are interesting.
Yeah.
Yes, this is not the case of World Championship where you fight already for the first position.
Yeah.
Okay, guys, thank you for a very nice discussion, but let me close the session, right? I would like just to remind that in 2 weeks, we will have a presentation by Erwin Pesch from University of Siegen. Erwin will speak about conflict-free crane scheduling in a seaport terminal, and hope to meet all of you on May 24th. Thank you very much for watching the seminar and being with us, and see you in 2 weeks. Thank you. Bye-bye.
Thank you.
Bye-bye.
Thank you.
Bye-bye.
Bye-bye.
Thank you.